The rate of heat generation by growth is given by QGR. In order to identify the total rate of heat evolution in a batch fermentation, can use the equation of QGR equals to VL, VL is the liquid volume, times mu net times X times 1 over YH. In aerobic fermentations, the rate of metabolic heat evolution can roughly be correlated to the rate of oxygen uptake, which given by QGR equals to 0.12 QO2, where QGR is in kilocal over H and QO2 is in millimole of O2 over H. The metabolic heat release during fermentation, it can be removed by circulating cooling water through a cooling coil within the fermenter or by using a cooling jacket surrounding the fermenter. Okay, this is related to the fermenter design. You can have a cooling coil or you can also have a cooling jacket. Okay, now we are going to look on the effect of dissolved oxygen on cell growth. The oxygen is required for the aerobic bacteria. Okay, therefore, if for the aerobic bacteria, we need to know the oxygen uptake and transfer for the fermentation. Okay. At high cell concentrations, the rate of oxygen consumption, it may exceed the rate of oxygen being supplied in the fermentation. When the oxygen is the rate limiting factor, the specific growth rate will vary with dissolved oxygen according to saturation kinetics based on the Michaelis-Menten kinetics. Alright. So below a critical concentration, the growth will approach a first order rate dependent on dissolved oxygen, which is oxygen is a limiting substrate. Okay, this is mainly for aerobic bacteria. Above a critical concentration, what happens? The growth rate, it becomes independent of dissolved oxygen, which means the oxygen is a non-limiting. Okay, diagram here shows the obligate aerobic cells and the facultative aerobic cells. Alright, so what is obligate or aerobic cells? Okay, the obligate or aerobic cells means that these cells, it requires oxygen. Okay, but for the facultative cells, it can have oxygen or also it can also live in the condition without oxygen. Okay, that's what we call a facultative. Right. So you can see the dissolved oxygen for these obligate aerobic cells, A. vanillide. Okay. So based on the specific growth rate here, okay, it's growing, okay, with the increment of dissolved oxygen, okay, until a saturation kinetics occur. For the facultative aerobic cells, okay, the requirement of dissolved oxygen, okay, it is needed. Okay, what happened? Until certain end of dissolved oxygen, it will move towards the saturation kinetics. Okay. The saturated dissolved oxygen concentration for water at 25 degrees C and 1 atm is 7 ppm. The presence of dissolved salt and organic can alter the saturation value, and increasing of temperature will decrease the saturation value. Dissolved oxygen here, we're referring to water because in order to prepare a medium, okay, the base medium, okay, the liquid that we require is water. Okay, so any kind of substrate, any kind of nutrients, okay, required for the cell, for the bacteria, is being dissolved in the water. Okay, in water. Therefore, the dissolved saturated oxygen is referred to dissolved oxygen in water. Okay. So the critical oxygen concentration is about 5 to 10% of the saturated dissolved concentration for bacteria and yeast, and about 10% to 50% of dissolved oxygen saturated for moles, okay, since they grow as large sphere in suspended culture. Okay, so this critical oxygen concentration is important because there is a level of oxygen, okay, that must be sustained in the fermentation. If it is decreasing until 0%, then your microbes, okay, can die. Okay, can die, right? So 10% of critical oxygen, okay, is a suitable level of a critical oxygen that is required in the fermentation. Okay, so we need to make sure that the transfer of oxygen inside the fermentation is suitable for the microbes to uptake in order for them to grow. Oxygen is usually being introduced to the fermentation through a sparger at the bottom of the fermenter. Okay, they're sparging air through the broth. Broth here, it means that a mix of water and all the nutrients or substrate that being dissolved in the water. So we mix all this together and it is called as broth, right? Media. Okay. So oxygen transfer from gas bubbles to cell is usually limited by oxygen transfer through the liquid film surrounding the bubbles, because we know that the oxygen is being introduced in a bubble form, okay, by sparging air. So air here, usually in the fermentation process, we are using compressed air, okay, because we are using a compressor to supply the air into the fermenter, right? The rate of oxygen transfer, or it is also known as OTR, from the gas to liquid phase is given by NO2 equals to KLA times C star minus CL, alright? Or usually it is written as OTR equals to KLA C star minus CL, right? Where KL is the oxygen transfer coefficient, A is the gas liquid interfacial area. Okay, if it is combination of KLA, it is known as volumetric oxygen transfer coefficient, which is, okay, this variables parameters is important in the mass transfer in the fermenter for the aerobic fermentation, KLA. Okay, and C star is the saturated dissolved oxygen concentration, okay, usually referring in water, okay, and CL is the actual dissolved concentration in the broth, okay, which is being recorded during the fermentation, okay, and NO2 is the rate of oxygen transfer if it is an OTR, okay. Okay, for the OUR, oxygen uptake rate, it is given by QO2 times X, or equals to mu G times X over coefficient of X over O2, YX over O2. Okay, this is the equation where QO2 is the specific rate of oxygen consumption and YXO2 is the yield coefficient of the cell over oxygen required, okay, and X is the cell concentration. Okay, dW is the dry weight. Okay, usually the cell concentration is being measured in the cell dry weight. Okay, when the oxygen transfer is rate limiting step, okay, what happened? The rate of oxygen consumption, it will be equal to the rate of oxygen transfer. It means that when the oxygen transfer is limiting, the rate of oxygen consumption is uptake, OUR, will be equivalent to OTR. Okay, so the growth rate varies nearly linearly with OTR under oxygen transfer limitation.